We're looking at titrations today, and what I'm looking at is the basic principles of a titration. So this is aimed at students who are perhaps doing GCSE, perhaps separate sciences for AQA, or if you're doing A-level and you're really getting stuck with titrations and getting confused by just how much information you get given in a question. So a titration is all about working out the concentration of a solution in a flask. That's what it really comes down to. Now sometimes there's an earlier step where perhaps you've been given the solute as a solid form and you've dissolved it to form that, but I'm going to start the story at the point where you've got a solution, you don't know the concentration, and you want to figure out what it is. You'll have worked out what's in the solution because you'll have done flame tests perhaps, or done some tests for maybe halide ions or for different ions, those different tests that you have to learn for exams. So you've worked out what it is, we want to know the concentration. That's what it comes down to. So I'm going to make a simple comparison here. So imagine we've got a dog's home. The dogs are all running around like crazy. We obviously want a home. And what we've got is an unknown and uncountable number of dogs inside. Now one way to figure out how many dogs there are would be to have an open day and have a queue of families waiting to adopt a dog. And what we're going to assume is that each family adopts one dog. So if that was a chemical reaction, it would be something like this. Dog plus family produces a happy ending. Okay, so let's start this. So we have the families outside, and all we have to do is let them in one at a time and count them as they go in the building. 1, 2, 3, 4, 5, 6, 7, and 8. Now when we get to this point, which will be called equivalent if it was a chemical reaction, and the reaction is complete, we do need a nice clear sign to stop. Okay, so to stop letting families in. So I'm just going to have a closed sign in this scenario. Okay, that would be an indicator in titration, so something that's going to change colour fundamentally. There are electronic ways to do it as well, but let's just keep it simple. A nice indicator that changes colour to tell you when you've reached equivalence, when you've reached the end of a reaction and you stop adding from the burette. So if you've counted those families going in, you've worked out how many dogs there were inside the kennels. Seems simple enough. So what makes it complicated? Okay, well, first complication with titrations in chemistry is we can't just count particles. Now, there's lots of tools that chemistry's got to get around that problem. Probably the most basic one is we don't try and count individual particles of reactants. We count moles of them. Yeah, we count 6 times 10 to the 23 of them. We count them in big groups. Now, the mole potentially is quite a confusing topic, but just think of it as the group now for particles. Yeah, so you can have a team of football players, and that will happen to be 11. You can have a team of rugby players, which can be 13 or 15. You might have a squad of American football players, which I think is 45. It's just a group now for particles, the mole. And yes, it's a particular number. It's 6 times 10 to the 23. But that's not actually too important most of the time. All that matters is that's what we're working in. And it's the same number of particles, whatever kind of chemical we're talking about. So our second trick for working out numbers of particles is we use concentrations. Now if you know the concentration of a solution you've been given because your lab technician has helpfully made it up to a particular concentration for you, that's a whole other topic. In A-level they have to learn about how to make standard solutions, and that's what that technique's called. If you know the concentration and you know the volume, then you can multiply those two things together and that will tell you how many moles are in the solution. So that's our first little complication. Now the second one is all about how you measure how much of the chemical you know about you've added to get the reaction to finish. So with our counting families going in, that was easy enough, but with chemicals, I mean in principle you could do a titration you could just have a beaker with your unknown chemical in it or your unknown concentration in it. You could have just a measuring cylinder with the one that you do know, and you could add small amounts from the measuring cylinder and stir and watch the indicator, and when the indicator changes then you'd stop adding from the measuring cylinder. The thing is that wouldn't be very precise, but it would give you a rough idea of what the concentration was. But what we use in chemistry normally are burettes, which have got a very good precision. I'll have some photographs of that in a second. Now what we do is you fill up the burette, you take a reading of it, you add from the burette until the reaction is complete. Once the indicator changes colour you stop and you take the two readings and take the difference. Now back in our adopting dog story, that's as simple as you're counting how many families you've got in the queue to start with. You let them in. As soon as the close sign goes up, you count how many families you've got left, and you take the difference. Now let's have a look how that translates to actual chemical equipment. So with a burette, it's a pretty good illustration of one on the left. you can see one thing is that the numbers increase as you go down towards the floor, because it's measuring how much you've added. Now there is a little subtlety here, which is you do need to make sure you read the bottom of the slope. The thing about a solution in the burette is it's probably dissolved in water, and water is by definition wet, which means it adheres to things, it's sticky. And if you're doing A-level biology, that's one of the properties of water you have to find out about. But that means you get this meniscus shape, this curve as it sticks to the plastic or the glass of the burette. So you read the bottom of this curve, the meniscus curve, you read the bottom, which means you do need to get your eye to the right level. So looking at this example here, the eye in the middle has got it right because they're looking straight across and they're reading correctly. Now because the numbers go down, then it's 19.1, 2, 3, 4, 5, 6, 7. So that's where we've got this value of 19.70. I've got a couple of photographs here. So this is a real burette. This is before and after. And what I'd like you to do is to work out the measurement or take the reading before the chemicals were added to complete the reaction, the reading after, and therefore what the titer is, or how much volume has been added. Now this person was trying to be quite clever, and bizarrely they've sort of double bluffed and got it right, even though they made a mistake. So what they were trying to do here was, I think they were trying to fill the burette up to 0 to make their life a little easier, because then the reading on the burette would be the amount they'd added. Now as it turns out, the bottom of the meniscus, I think, is at 0.2. But they've got the top of the meniscus at 0. It's actually worked out for them because excuse me, it's actually worked out for them because the final value on the burette is 22, and reading across from the bottom of the meniscus is 22.2. So the difference between those is 22.0. This one's in millilitres, but we'll have a little conversation about that in a second. But a millilitre and a centimetre cubed are the same size. I mean, if they've read the top of the meniscus, they're actually still going to get the correct answer. But they were fortunate with that one. Okay, so that's sort of a problem. Now, often these titration problems, especially A-level students, find have got lots of information in that you don't need. I've just edited out the bits we actually need to know. So we've got 22 centimetres cubed of alkali from the burette. We've got 25 centimetres cubed of the acid at the bottom. This is the thing that we don't know the concentration of, but we can measure out the volume very, very precisely using a pipette. It doesn't actually matter too much what the acid and the alkali are in this story, as long as we know what the numbers are, the balancing numbers in the equation. And it's a 1 acid and 1 alkali react together. Very conveniently, the concentration of the alkali the technician gave us was 1 mole per decimetre cubed. And so we were trying to figure out the concentration of the acid. So the first step in any titration equation is always work out how many moles you added from the burette. And if you're doing A-level, this is a guaranteed mark. Okay, so moles added will be the concentration times the volume. Okay, which is a concentration that we know about. It's 1.0. And the volume is 22. Now we do have a small problem here that comes up. Concentrations are given in decimetre cubed, or moles per decimetre cubed, which is the same size as a litre. But a decimetre cubed, often forgotten, is a tenth of a metre, or 10 centimetres. So a decimetre cubed is literally 10 by 10 by 10 as a cube, which is 1,000 centimetres cubed. Okay, so we're going to have to correct for that when we're working with our calculations, and this becomes second nature after a while. Okay, so just need to let's just rub out some of those unnecessary circles. We don't need that one. We don't need that one. Okay, back to pen. Okay, so we've added 22 centimetres cubed, but that is 22 thousandths of a decimetre cubed. Okay, so you'll get used to dividing by 1,000 to convert centimetres cubed to decimetres cubed. Okay, which I think is going to be, let's see now, 1 times 22 over 1,000 is going to be 0.022 moles. Okay, next step, we've figured out. Alright, just grabbing a calculator. We've been given the equation here. We might have to work it out sometimes, but this is the number of moles of alkali that we added, so we know that for sure. And we know from the equation that one acid reacts with one alkali. So the number of moles of acid equals the number of moles of alkali. So down in that conical flask in the bottom there, the moles of acid was the same as the moles of alkali. Equals 0.022. And then finally, we do want to know what the concentration of the acid is. So we go back to that equation that you will use so many times if you do A-level chemistry, which is number of moles is concentration times volume. So the concentration is the moles, number of moles, divided by the volume, which is 0.022. And then the volume in here, it's the volume that the acid was dissolved in, was 25 centimeters cubed. And there's our friendly conversion factor again. Okie dokie, so 0.022 divided by brackets 25 divided by 1000, and we get 0.88 moles per decimeter cubed, or if you're doing A level, moles dm to the -3. And that seems to make sense. Is that the right way around? Let's see now. We had to add slightly less alkali than acid to neutralize it. Looking back at the original figures, the 22 and the 25. So that tells me that the alkali was a bit more concentrated than the acid. And that's right, the alkali was 1 mole per decimeter cubed, and the acid has come out as a slightly smaller value. Final thought, complication, there's the whole section about how to take the readings on a burette and the idea of concordance, but let's just assume that we've been given those values. But the final complication that you get in a simple titration is this one, which is where the reaction isn't 1-to-1. So I've just taken the same problem, but in this one we've got 2 moles of acid reacting with 1 mole of alkali. Okay, so still the same basic step. So we work out how many moles we've added from the burette, the known moles. So that's the concentration times the volume, which is 1.00, and the volume is 22 over 1000. So we still added the same number of moles of alkali. Okay, then we use the ratio part, and we need to look back at the equation and we see that we have 2 acid with 1 alkali, which means that the acid number of moles is 2 times the alkali number of moles. So we've worked out the moles of alkali in line 1, so the acid is actually double that. Now you get all sorts of variations with these ratios, but if you actually just step back and look at the actual values and say, right, which one do I know? I know the alkali moles, and the acid mole is double that. Sometimes you get 5-to-3 ratios, 5-to-2, especially at A level. For GCSE, most of the time the reaction is going to be 1-to-1, and if the worst comes to the worst of a titration calculation, just assume it's a 1-to-1 ratio. If you can't pick out the values, use 1-to-1 anyway, because at least you'll be able to work the question through to the end and get most of the marks. Okay, so we need 2 acids alkali, so we're going to have 0.044 moles of acid, and then to get to a concentration, the number of moles divided by the volume, which is 0.044. Remember, we're talking about the acid, which was in here, the 25 centimeter cubed sample. So I reach for my calculator, and 0.044 moles divided by 25 divided by 1000. That's 1.76. And again, moles per decimeter cubed, or moles dm to the -3. Okay, does that make sense? Let's have a look. Look back at the reaction. We needed a lot more acid than alkali, so we used roughly the same volume of each one, to get to neutralise. But looking at the reaction, the acid needs twice as much. Okay, there's twice as much acid as alkali required. So that would make sense. If we use the same volume, the acid must have been more concentrated to make that work. Back in the dog system, I guess that's one family adopting 2 dogs. I don't want to go there because I've got dogs on my mind now, homeless dogs. Let's move on to the close of this. Okay, so a little summary here. Titration, it's all about figuring out the concentration of an unknown species, which you're probably going to put in a conical flask at the bottom, and you're probably going to know what's in the burette. So, our simple model, we had a dog that was homeless, we had a dog living family, we mixed those 2 together, and the indicator, because you need to know when the reaction is complete, is that closed sign. Now the most common titration you're going to come across, certainly at GCSE, is acid and alkali, or acid and base. And if we look at that very simply, an acid, which is a proton donator, and an alkali, which is taking protons, you put those 2 things together, you can get a reaction. The indicators you use to tell you when the reaction is complete, you could use your universal indicator, I suppose, and look for it turning green to tell you when it's neutralised, but it's not ideal because they've got so many ranges of colour. So we tend to use single colour indicators, or indicators just have 2 distinct colours. Methyl orange is one we use quite a lot, and phenolphthalein as well. A third kind of titration, well, a second chemical titration that A-level students learn about, and I think you're going to like the symmetry of this, is we sometimes titrate oxidizing agents and reducing agents. So for example, the solution that we don't know is one of those 2. And if you look at that in very simple terms, oxidizing agents accept protons because the other species has given it to them, so it's lost them, and reducing agents donate protons. So you could mix those 2 things together and get a reaction. It's called a redox reaction in A-level chemistry. Now the indicators we use there are potassium permanganate, or we use iodine and starch. But it's still the same basic principle. We've got 2 chemicals that react together and an indicator to tell us when the reaction is complete. So I hope that's helped you if you're finding titrations quite a difficult idea. Ultimately, it's as simple as you've got some chemical in a pot that you don't know the concentration of. You've got a chemical in something that you can measure the volume of that you do know the concentration of, and an indicator to tell you when the reaction is finished.